Hello. Now we'll do the moment of inertia. We'll calculate the moment of inertia for hollow cylinder. So this is our hollow cylinder and its mass is given m and its radius is capital R. So this is hollow basically. So there is nothing here in this region. So cylinder is having this. This is negligible thickness basically. We have just shown it here, but the thickness of this cylinder is negligible. So yeah. Okay. So we want to calculate the moment of inertia for this hollow cylinder about this axis. You see, this axis is passing through the axis of the hollow cylinder. So this axis and the axis of the hollow cylinder, they are same. So we want to calculate the moment of inertia of the hollow cylinder about the axis which is perpendicular to the cross section area and passing through the center of mass. It will be passing through here. Okay. We want to calculate this. So to calculate the moment of inertia, we have to first cut this hollow cylinder into the elements. Elements are the object by which you can recreate this hollow cylinder. Okay. So in this case, what we will do, we will cut this hollow cylinder into the rings. Okay. You see, if you cut this hollow cylinder, you will be getting multiple rings. And if you join all those rings, you will be having the hollow cylinder. Same is with the solid cylinder also. If you cut the solid cylinder, you will be getting the disc. Okay. So with the use of disc, you create the solid cylinder. So the difference in hollow cylinder and the ring is only just this thickness. So in this case, the length of the hollow cylinder is L. So when this L will become 0, this hollow cylinder will convert into a ring. Okay. So we want to calculate moment of inertia for that. So let's cut a ring or let's cut an element here. So to cut the element, I'll be from one of the corner, I'll be moving till distance x. So I move till distance x. And after moving till distance x, I'll cut this cylinder with the help of a cross section area. I cut it like this. So this is one of the cross section area. So I moved along the x. Then I further move by dx. If I further move by dx, one more time I'll cut it. So between these two cuts, I'll be having this element. So you see, this element is not linear element. You see it from here, it might look like linear element. But when you take it out, when you take this element out, it will be nothing but a ring. Ring of mass dm and the radius capital R. This ring will be having the same radius as the radius of this hollow cylinder. And its mass will be a little bit less. I'm calling it dm. The thickness, this thickness, meaning thickness is inside in the plane. So this is this view. So if I'm looking from this side, this portion will look like this. Okay. And thickness of this ring is dx. Okay. So this is my ring and I want to calculate the mass of this ring because ultimately if you keep joining these rings, you'll be creating the hollow cylinder. Okay. And one more thing, this axis will be perpendicular to the plane of the ring and it will be passing through the center of mass of the ring. You see this one. If you take it out, ultimately it is passing through the center of mass of the ring and perpendicular to this ring. So first, we want to calculate this mass of this ring. To calculate the mass, first we have to calculate the density of this hollow cylinder. So hollow cylinder, all the mass is distributed over to the cross section area. So here I'll not be going by the volumetric density, I'll be going by the areal density here. So I'll define the areal density. So areal density, we define it by sigma. And the thing is, I'll be assuming that this mass is distributed uniformly onto this hollow cylinder. Okay, so if this mass is distributed uniformly over to the hollow cylinder, to calculate the density, I'll divide the mass by its total cross section area. Total cross section area where the mass is there. So there is no mass in this region, you see. This is not closed. This is also not closed. So I'll be taking the cross section area which is this side of area. If this is the hollow cylinder, I'm talking about this area only. To calculate this area, okay, how to calculate this area? There comes the question. So if this is your hollow cylinder, this is your cylinder. If we cut the hollow cylinder from here and if we open it, so if we cut it from here, if we cut this hollow cylinder from here and if we open it, ultimately this hollow cylinder will open into a rectangle. So what I'm doing, I'm cutting it from here and I'm opening it. So when you cut it from here, this is going to be the length. We are cutting it from here. So keeping this intact, I'm opening this portion. So if I will be opening this portion, this length will be equals to the total periphery and which is 2 pi r. So the areal density will be m upon 2 pi r one side multiplied with L. This is equation 1. So after calculating the areal density, I can calculate the mass of the ring. So the mass of the ring will be equals to areal density multiplied with area of the ring. So area of the ring, you see again one more time, this ring is there. If I cut this and if I open it, it will also be like a rectangle. But this time the thickness will not be L, but it will be dx. This dimension will be equals to dx. But this dimension will remain same. So sigma into area will be 2 pi r, because this dimension is going to be same for even this ring, and this will be equals to dx. So let's put the values here. M upon 2 pi r L into 2 pi capital R dx. This 2 pi r and 2 pi r will cancel out. So this dm will be equals to m by L times of dx. So this becomes the mass of the element, which is a ring element. Now I need to calculate the moment of inertia of this ring element about the axis which is passing through the center of mass. So if you remember, we had a formula. Moment of inertia for a ring was equals to mr squared. That was the formula for moment of inertia of a ring about the axis which is perpendicular to the ring and passing through center of mass, which is the same ring here also. In this formula, m was the mass of this ring and capital R was the radius of the ring. In this case, mass is dm and the radius is capital R. So now I'll define the moment of inertia of this element dio about this axis. So that will be equals to mass of the ring dm multiplied with capital R square, because the capital R is the radius of the ring also. Let's put the values. So it will be m upon L R square dx. That will become the moment of inertia. This is equation 2. This becomes the moment of inertia for my element about this axis. To calculate the moment of inertia for the whole, hollow cylinder, I need to integrate moment of inertia of the element. So, and we have to integrate in such a manner so that the whole object should be covered, which is a hollow cylinder. So let's put the values. Let's integrate this value. So m capital R square upon L. You see, variable is dx here. So mass, capital R and L, they are independent of dx. As you will be changing the value of x, the mass of the cylinder, radius of the cylinder, and the length of the cylinder is not going to change. So we'll be taking it out of the integration sign. Inside there will be dx. And the limit will be from 0 to L, because ultimately x will be starting from this point and it will move till the last point. So it will be mr square upon L. Integration of dx will give you x 0 to L. mr square by L. Let's put the limit. So first we'll replace this variable by the upper limit, which is L, minus then we'll replace this variable by the lower limit, which is 0. That's how we integrate, definite integration actually. So moment of inertia of the body, this L and L will cancel out, will be equals to mr square. Okay. So as you can see, we have calculated the moment of inertia for the hollow cylinder and the formula is equals to mr square. It is similar to the ring also. Because see, there is no difference between this hollow cylinder and a ring except one, this. So if I change this L into a dx, this whole thing will become a ring. So there is, if I am having a ring and if I make it large, if I make this thickness which is negligible into a big thickness, this ring will convert into a hollow cylinder basically. The only difference is L. So the formula, that's why the formula is not changing at all. The formula only, here the mass is for the ring, here the mass is for the this whole body. So only mass is changing, the remaining formula remains same here. And if you remember, while deriving this thing, we have assumed one thing, and that thing is the areal density. So while deriving this formula, we have assumed this areal density to remain constant. So if the areal density is going to change, from here itself will change the process. Process will remain same, the formula will be changing. We'll not be writing areal density as m upon 2 pi RL, we'll be writing which is given in the question. Okay. So based upon that, obviously the value for moment of inertia will change. Okay. So that is your moment of inertia for the hollow cylinder. and you should be memorizing this also. It will be better for you. And this moment of inertia is being calculated about this axis and this axis alone. If you are going to change the axis, obviously the formula is going to change, because moment of inertia is not a scalar quantity. It is a scalar once you fix the axis. So this is the moment of inertia for the hollow cylinder about the axis passing through the axis of hollow cylinder. Okay, thank you.